In this lesson we're going to look at the latent heat of vaporization. In the last lesson we looked at the latent heat of fusion, and we're going to continue with our same substance, this mysterious orange substance, which is a pure substance here, and at the moment it's in the liquid state. Okay, and what has happened is we've heated it up. It was a solid, we've heated it up, the solid melted completely into a liquid, and we've continued heating, and we're heating and heating and heating, and now we've reached the point where it begins to boil, just at this point here. So we've reached the boiling point. Okay, now although particles are evaporating from the liquid even when it isn't boiling, at the boiling point the evaporation process starts to take place at the fastest rate. So we recognize this boiling point again immediately by this flat bit in the temperature time curve, and remembering our particle model, this is the point at which particles start to escape from the liquid state into the gas. And in escaping, what's happening is that they're being heated. So heat's going into the liquid, right? Heat's being absorbed by the liquid during this boiling process, and the energy that's going into the liquid is being used to help the particles overcome the cohesive forces within the liquid so that they can escape into the gas state. Okay, and this heat that's being absorbed by the liquid during this process is called latent heat, and in this case it's the latent heat of vaporization because it's helping the particles to evaporate. So as we mentioned, this is an endothermic process. Okay, that's to say heat is being absorbed to help those particles overcome the cohesive forces. Now what we want to do here is to write a formula for this latent heat of vaporization, to give a definition for it first. Okay, so we can say that the latent heat of vaporization is the heat absorbed at the boiling point of the substance to completely convert 1 kilogram of liquid into a gas. Right, so that's a simple definition, it's a straightforward definition, and we can write, as with the latent heat of fusion, we can write a fairly straightforward equation to define this latent heat. So we can write L for latent heat, and this time it's V for vaporization rather than F for fusion. That's what's going on down here, and that's equal to, okay, here the heat absorbed, so that's Q. Okay, that's the heat that goes into the liquid during this boiling process, okay, divided by the mass of the liquid present. Okay, and as before, the heat is measured in joules and the mass in kilograms, so the unit for latent heat of vaporization is joules per kilogram. Okay, so put that in a box to safeguard it so we can see it clearly. That's the important equation that we've got to remember when we're doing our latent heat of vaporization calculations. Okay, so just as heat is absorbed when the liquid is in a process of changing from the liquid into the gas, that's to say when it's boiling, so also heat is released when the gas is in the process of changing back into the liquid. That's to say when condensation is occurring, and in this case this process is an exothermic process. So boiling is an endothermic process, a term from chemistry, and condensation is an exothermic process. That's to say heat is given out. Okay, and it's the same heat that is taken in to help the liquid completely evaporate is the same heat. Okay, it's the same latent heat of vaporization that is given out when the gas condenses into a liquid. This is the same latent heat of vaporization. So in this case it's the heat released rather than absorbed as it was before at the boiling point to completely convert 1 kilogram of gas into 1 kilogram of liquid. Now that is why, steam, for example, if you're cooking, can be very dangerous indeed, because when steam hits your hand or your arm and that condenses into a liquid, well, all of this latent heat contained within the steam is released into your arm in order to help the gas condense. So steam can be very dangerous because of this latent heat that it will be released in the condensation process. Okay, so let's just have a look at a quick kind of calculation to do with latent heat. So we've got this beaker of 350 milliliters of water and we've just brought it up to the boil, so it's just started boiling, and we want to ask ourselves how much heat here is required to completely evaporate the water from the beaker. Okay, so to do that we need to know what the latent heat of vaporization is for water, which I'll have to look on my mobile phone to find that out, I'm afraid. So you have to bear with me. So as in any physics problem, just about any physics problem that you come up with, you've got to look at it and you've got to decide which equation you're going to use or you're going to apply to solve that problem. So we're going to use the equation for the latent heat, LV equals Q divided by M, and LV is a constant that we'll get from a reference book or from Google, which I've done in this case, which is the heat required to evaporate exactly 1 kilogram of water at the boiling point, and that value LV is equal to 2260 kilojoules per kilogram. Okay, and we need to watch here. We've got 350 milliliters of water, and we know that 1 milliliter of water weighs exactly 1 gram because the density of water is 1 gram per milliliter. But we've got to remember here that we've got kilograms here, so we can't mix the units. We need to change this to kilograms, which is equal to 0.35 kilograms. And there we have it. All we need to do now is rearrange the equation. We want to find the heat supplied. Okay, so that's Q is equal to the latent heat of vaporization constant times the mass of liquid, which is equal to 2260 times 1,000. That's what that K means, that's 1,000 times 0.35, and that gives us 791,000 joules, or 791 kilojoules of heat. Okay, so to boil all that water, to evaporate all that water once it started boiling, right, requires 791 kilojoules.